Welcome everyone. In today's class we will start learning computational tree logic. So, if you remember, in the last few classes we start out linear temporal logic, where we see the property which defines over a path, right. So, on the other hand, in the computational tree logic, the property will be defined over a branch, right, in a tree, right. So, multiple possible execution path. Okay. So, that is the fundamental difference between LTL and CTL, right. So, if you think about a LTL, we will always consider a path, and I will see whether whatever the property I am talking about, it holds in that infinite path or not. But whenever I am talking about a CTL, I will take a computational tree, right. It can be something like this, right, and so on. So, now I will have multiple path, this is one path, this is one path, and these are all infinite path, right. So, I am just drawing some part of it, this is another path, this is another path. So, I have to think about all paths starting from this node, right. So, now why do we need such things is basically how do you visualize your system. So, remember when I was talking about this property, we are going to check this property on a system, right, in a for some circuit, and what we have discussed in the previous classes, from that circuit we extract a state machine. So, effectively you have a state machine, right, and the state machine have multiple paths. The question is, how do you visualize your execution? In LTL, whenever I am talking about this linear temporal logic, I always consider a single path, one execution path, and I will see how the property holds in that, right. It is basically a path property. On the other hand, CTL, I am now actually from the start node I am expanding in all directions, and I effectively construct a tree which basically consists of multiple computation path, and then I am going to visualize, or I am going to check my property on all possible paths, right. That is the difference. In today's class, we will primarily introduce the CTL, and subsequent classes we will talk about the syntax, semantics and other part of CTL. Okay. So, as I mentioned, it is basically branching time temporal logic, or CTL full form is computational tree logic. So, it basically you visualize your time in a branch in a tree, and then you check whether the property holds there or not, right. So, this time is viewed as a computation tree, and multiple future execution path is possible, because in a tree there are multiple paths, and because there are multiple paths, we have introduced two path quantifier, right. So, effectively we have introduced A and E. A means for all, right. So, basically in for all paths, and E means there exists a path. Okay. So, whenever I am talking about a computation tree like this, right. So, I can have different tree. I am just drawing some part. Now, I am checking some property, say this is my S0, right. If I am checking certain property at S0, whether I will check that property in all path or at least one path, that is something we have to quantify, because there are many paths now. Okay. So, we have two path quantifiers, A and E. So, if I now try to formally define this CTL, let us now define computational tree logic properly. So, we have seen LTL. In LTL, what we have? We have atomic propositions like P, Q, reset, start, and so on, any proposition, and then you have Boolean connectives like negation, conjunction, disjunction, or implication, right. And we have four temporal operator that we have already seen in LTL, which is X, which is the next state, F is eventually or in some future state, G is globally, means in all state, all future states, and until is something one holds until something else hold, right. So, there are four temporal operator, and we have already seen writing property with these temporal operators, right. So, this part is effectively LTL, right. This is the consist of LTL. In addition, we have this path quantifier A and E. So, A means for all path, and E means there exists a path, right. So, this is basically the component of CTL. So, whatever we have learned in LTL, we will have only path quantifier along with, but the formula will be different, right. You cannot have any formula without any path quantifier, right. So, this is something we will learn. So, that is the syntax, what is the correct way of writing formula in CTL, right. So, we learn the syntax of CTL. So, as I mentioned that any atomic proposition is basically a CTL formula, right. And then if you have two CTL formula phi and psi say, and then if I take a negation of the formula, that is also a CTL formula. So, effectively if you remember what is syntax, it is just basically check what are the correct way of writing the formulas, right. So, on the other hand, semantics is basically meaning of the formula, right, what does it mean. Okay. So, syntax is I will discuss now is if there are two formula phi and psi, their conjunction is also a CTL formula, right. And then if you have two formula, their disjunction is also a CTL formula, right. Individually they are CTL formula, valid CTL formula. If I do a conjunction, disjunction or implication, they are also become a valid CTL formula. Okay. But most importantly, how this path quantifier for all and there exist A and E get bound with the X and F and G and U is important. So, here if you remember there are four path quantifier X, G, F and U, right. So, in LTL we have defined what is the meaning of them. Now, in CTL it is very important to note that they cannot occur independently, right. The previous one is basically the Boolean connections, we are not talking about any path quantifier yet, right. But independently this can be a formula where you have path quantifier, right. It can be like A F phi implies A G say psi, something like this. So, this is my phi and this is say psi. So, if this is a CTL formula, this is a CTL formula, their implication is a CTL formula, right. This is what I mean here. But very important to note here that this temporal operator always be bind closely with a path quantifier, right. So, earlier I have only syntax for X, G, F and U in LTL, but in CTL we will have into two, right, into A and E, right. So, this is basically it will give you 8 combinations, right. So, it is basically AX, AX, EX, right, AG, EG, AF, EF and AU and EU. So, there are 8 possibilities, right. So, and you have to remember that this always temporal operator will be closely connected with a path quantifier. Okay. Now, let us understand what the meaning of AX. So, there are 8 combinations just I talked about. Let us understand their meaning, right. So, what is AX? You know AXP, right. So, I am writing here. So, you can ignore the parenthesis here. Okay. So, this P or it can be some formula phi, right. It can be AX phi, where phi is already a CTL formula, right, or it can be just a proposition P. Individual proposition is also CTL formula, right. So, whenever I am talking about AXP, what does it mean? I am saying that in a branching tree, I am in the root node, in all path starting from this node, all the next node satisfies P, because there is for all, right. So, that means in all path starting from my current node, in the next state satisfy P or maybe psi or phi, right. So, if I try to give an example, let us say I have a branching tree like this, right. I am taking a very simple example, right. Let me I have said this one and then I have, right. Now, I am saying that from this node, right, because this is my starting node. So, I am saying that AXP means how there are many paths possible, right, that I have already talked about. From here there are many paths, right. So, in all path will start from this and either will go through this edge or this edge, right. There are many paths. So, now I am saying ki all path in the next state P must hold, right. So, if P holds here, P holds here, then I will say this particular model, so this is S0, I will say S0 model S0 satisfies AXP, right, because in all next state P holds. Similarly, EXP. So, here E means there exists a path. So, there are many paths That means there is at least one path, there exists a path in which in next state P satisfies, right. So, if I now take the same example, so in this case also, so this is satisfied because there are all paths, all next state it satisfies, means at least one path also satisfies. So, I can write here M S0 satisfies Ex as well, Exp as well, right. Now, it may be the case that not all is in all state this is there, right. So, I just have this in only one state it is true, right. I have only one state, one next state where P holds. In that case also this holds, but this does not hold, right, because it is not that all next state in all path in next state P holds. So, there is some path here which is going through this node, this node. In that case next state P does not hold. Okay. So, I hope you understood. It is basically the next state only whether you want to check for all path or in one path, right, at least one path. Similarly, if I understand this, I can easily identify AF and EF. I know F is eventual, that means in some future state. Now, let us take the same example again. Let us say I have the same example, let us say I have this, and let us say I have P holds somewhere, right. So, let us say P holds here, P holds here, and so on, right. So, I have these three state P holds. Okay. Now, I am checking AFP, it means in for all path in future P holds. Okay. So, now let us see here how many paths, there are many paths, right. This is one path, this is one path, right, this is one path, this is one path, right. So, let us say there are 4 paths. So, in all path in future P has to hold. Now, you think about this path, in this path in future P holds, because this is this in this state P holds. You think about this path, in this path also P holds in future. Now, here there are 2 paths, right, both paths P holds here. So, then that means in both cases P holds in future. So, in this particular example in all path in future P holds. So, I will say model S0 satisfy AFP. Okay. And similarly, if EFP is basically there exists a path where P eventually occurs. So, obviously, as I discussed, if AFP occurs, then that also satisfy EFP, right. So, in this particular example MS0 will satisfy EFP as well, because all path includes one path, right. But now, you think about I just remove this P. Okay. So, I do not have this P. So, I have this 2 P. Okay. So, now in this case I have P here and I have P here. Now, so there are one path where P holds in future, there is another path where P holds in future, but in this case in these 2 paths there is no P holds in future. So, in this particular example if I remove this P, so this is correct, but this is not correct. So, I will say MS0 does not satisfy all AFP, right. That means, in all path in future P holds is not true in this scenario. Okay. So, what I am basically visualizing here, I am always taking a branching tree and where some nodes, some properties are holds, some proposition holds, and I will see whether this AF all path or there exists a path and that particular property holds there or not. Okay. So, these two are we understood. Let me clear this diagram now, it become messy. Let us now consider AG. Okay. So, AG means G means global, right. So, if I think about in only in LTL, I will take a path in that path in all state P should hold. If I write this GP, right. If I write GP, it means globally P holds in that path. Now, I have just augmented with A, that means in all path globally P holds, right. Now, let us take me an example. Let us say I have taken another tree. The tree is basically the execution extension of a sequential state machine, right. So, FSM, I am just unrolling the FSM in different direction, right. I will give a concrete example later. Let us say I have this, I have say I make it a little bit complicated and there are a lot of states after that. Okay. So, I have this scenario. Now, in this case if I have to say AGP holds, okay, then this P has to hold in all path in all state. Effectively it means P has to hold in all state, right. If I P holds in all state, then only this will be true, right. I am assuming the state after that there also P holds, right. Now, what is the case here? I am saying that P always hold in all paths. So, what are the paths here? You think about this is one path, this is another path, this is another path, right. This is another path, this is another path. There are 5 paths I can identify here. In all path, in all state, P should hold. So, in this path all state P holds, in this path in all state P holds, in this path all path P holds, in this path all state P holds, here also, right. So, then I can write that this model, and this is my S0 state, S0 satisfy AGP, and as I mentioned, then this also satisfy EGP, because there exists a path in which globally P holds, right. Now, if I just remove one P from here, right, let us say I just remove this P, then this particular model does not satisfy this, because I found a path which is this is the path in which P does not hold globally, right. So, that means now if I just remove one path, I will say this is not true, but this is true, because I found one path in which P always true, okay. Makes sense. So, we have understood AG and EG. Now, this P, AP until Q and EP until Q, okay. So, here again P until Q you understand in a LTL context. Whenever I am thinking about LTL, it is a single path in which P holds until Q holds, right, but Q has to hold, right. So, that is P until Q. So, now if I just augment with A and E, it means all path that should hold, and E means there should be exist one path in which this P until Q phenomenon should hold, right. Now, let me take the same example probably, and let us say I just update this level. Let me remove some of the level, right. So, let us say I have this scenario now, and so I have this state, rest of the things are same, and let us say I have P until Q, right. So, I have Q here, I have Q here say, right, and say P here, P here, Q here, Q here. Let us say I have this scenario, then I will check whether both are holds here or not. So, now here you see in this path I have P holds until Q holds, right. So, in this path P until Q holds. So, I will always say that there exists a path in which this satisfied, right, EP until Q holds, right. So, I can just write this, that M is 0 satisfy E P until Q, because I found at least one path in which P until Q holds. But does it hold in all path? Example here, you just look into this example carefully and check. It is actually no, right, because I found this path in which in this state P does not hold. So, in this case P holds here, P holds here, P holds here, but P does not hold here, and then Q holds. So, P until Q does not true in this case, right. So, then if I have this example, I will say S0 does not satisfy A P until Q, right. But if I just add P here and Q here, then this is true, right. Now, in this path also P until Q holds. After Q holds, I don't need to check what, right. So, now again in this case P holds everywhere until Q holds in both scenario, this path as well as this path. Similarly, in this case P holds until Q holds, P holds until Q holds, right. So, if I have this scenario, then I will say this is actually satisfying, but if any of the path where this does not happen, then I will say this does not satisfy, okay. So, it is very important to understand the meaning of this, all these combinations, because now I am going to combine them and make a bigger formula, right. So, I hope this syntax is clear. So, just to summarize again LTL versus CTL, LTL is basically linear time logic, where I think about the time as a sequentially or linearly, right, in terms of path. On the other hand, in CTL, I consider time as a branch. I will basically explore all possible combinations, right. So, in this case I have a single path, so that means there is a single future path. Here there are multiple paths because there is branching time logic, right. Here I have no path quantifier, we have only 4 temporal operator, but here you have 2 path quantifier A and E, which is closely bind with all the temporal operator, right. Here it is basically path oriented, I always visualize everything in a path. Here it is tree, I will always construct a branching tree, and then I will visualize my property either on all path or in some path, or basically there exists some path, at least one path, right. So, just to give an example of this property. So, this is a LTL property, because if there is a request happen in future, you will get the grant, right. So, this is what we have discussed earlier also, and this is globally true. So, that means you are thinking about one path in which a request happen here, and then in future you get grant, right. In this case, if this is my pi, I will say pi satisfy this property, right, pi satisfy this property, which is said the property is a p, right. Now, if I rewrite this property in CTL, it will look like this. Why? Because here I have to bind all these temporal operator with a path quantifier. So, because what I am saying, whenever the request happen, that means in all globally, I mean all computation path globally. So, this automatically augmented with A, right. So, I get AG. If request happen from that state, whatever path going on in all path in future, grants should be there, right. So, this must hold. So, that is why I put AF here. So, you have to judiciously think about whether I should put A or E, but you have to add it. But in this case, the example I was talking about, that if request happen, eventually that should get the grant. It means in all path, all computation path globally, whenever request happen in some future state, in from that state, whatever the possible future state, you will get request, right. So, this is with the corresponding CTL property. Okay. So, remember here it is not something this LTL and CTL is something fighting each other. This is just a different convention, their algorithm is different, the way you are going to check the property is different, but they are basically, you can mostly encode everything which you can do in LTL, you can also do in CTL. There are some cases which cannot be done in LTL, but can be done in CTL. Similarly, there will be some example which can be done in CTL, but cannot be done in LTL, right. So, if you think about this is LTL, this is CTL, actually most part is common, this part is very less, this part is very less. There are very few corner cases which can be done only in CTL, but cannot be done in LTL and vice versa, but most of the property can be done in both. Okay. So, what I will do now, I will take few examples, because it is very important to understand the meaning of these properties, right, and what does this mean. So, what I will do now, I will take 5-6 example, and I will try to construct the branch tree to show that in what scenarios this will hold and what scenario this particular property does not hold, or what is the interpretation of that property essentially, right. So, let us start with the AG P implies AF Q, right. So, it is basically the same example, right. AG, if AGP implies, what does it mean? It means in all, this means all computation path, A means all computation path. So, I am now in a branching tree, I am in the root node, from there whatever the computation path in which globally, that means in all path in all state effectively, right. In all path globally, whenever P happens, P holds, whenever P holds from that state. So, I basically can think about, it may happen in some future state, it is not basically that you have to it hold, but whenever P holds from that state, right, all paths Q should eventually holds in future. Okay. So, let me give an example. Let us think about, I have okay. It can be anything, right. I just take some arbitrary branching tree. So, what I am saying here is that if, so all path, there are many paths here, right. In all path, if P holds, let us say P holds here, right. I am thinking about this path, right, p holds here. Whenever p holds in future, from there on, so from here there are two paths, this is one path and this is one path. In these two paths, q should hold in future. Think about, let me make it little bigger, right. So, let us say I have this. So, there are two paths here and let us say q holds here, q holds here. So, then this is for these scenarios, this holds, right. So, in this case p holds here, and from there on there are two paths in both cases, in all path in future. So, from here there are two paths and there in future q holds. So, this part holds for here, but similarly for this also it has to hold, because from here there are three paths, right. So, there are three paths here. So, this is one path, this is one path, this is one path. Let us say q holds here. So, this phenomenon holds for these scenarios. Let us say I have p holds here, okay, and q holds here. So, now you see here, this is the path in which whenever p holds, after that in all future paths starting from here, it has two path here and both case future q holds, right. Now, think about this path, right. There are third category of path, this path or this path. In this path p never holds, right. So, that means this is false. Then also this property holds, right, because in a p implies q, if this is false, automatically this is true, right. So, this is true. I do not care if this is true or false, this will always be true. So, if p does not hold in some path, then the property vacuously true. So, I have constructed an example in which this particular property a g p implies a f q holds. In some cases where p never holds, that means it is vacuously true, but whatever the path where p holds, from that state in all future state q holds, right. That happened for this part and this part. So, this in this case I will say, if this is S0, M S0 satisfy this property, right. If this property is p, this property is getting satisfied. Okay. Let me move on. So, now I am saying I am taking E, F, P and Q. What means? There exists a path in which in future there will be some state where P and both P and Q holds, right. So, that is what I have written here. There exists a computation path such that for some future state both P and Q holds, which is much easier to show. So, I will basically draw a, you can have many scenarios, right. I am just drawing one scenario to show this, right. So, let us say I have this, and in this state say I have P and Q holds, right, and this is my S0. So, then I can found one state in which in future state both P and Q holds. Then I will write this model S0 satisfy E, F, P and Q. There exists a state, there exists a path in which in future there is a state where both P and Q holds. This is easy, right. Let us move on. So, now I want to check this. This is also understood that there exists a computation path in which where P remains true until Q true in this path, right, but Q must eventually hold on that path, right. That is the property of P until Q. So, I can quickly construct a tree right. Think about this tree and let us say P holds here, right, P holds here, P holds here, and these are all infinite path, right. You have to, I am always drawing this, but you please remember these all are infinite, right. Your computation is going on forever, and let us say P holds here, Q holds here, right. After that I do not need to care. So, now I found one computation path in which P holds until Q holds, right. So, I will say that this S0, this model S0 satisfy E, P until Q, because this is the path. Okay. But if you do not any such path, they will say it does not exist. Okay. Now, take this one, this is AX, P or Q. This is very understood that for all computation path in next state either P holds or Q holds, right. Again this is very easy. So, I can always construct a tree let us say after that there are something. Now, let us say in this state say P holds and here p holes. Then also I can write this is my S0, I will say M S0 satisfy A, X, P or Q. Why? Because P is holding. So, I have to either P holds or Q holds, even if both can hold, right. Now, you think about a scenario where instead of P, you have P here also, right, Q. Then also I will say this is holds, or say I have a scenario where I have only Q here, then also I will say this holds. All these scenarios, this say ki because all path next state either P or Q holds, I can say that this particular branching logic satisfy this. Okay. Let us take one more. So, what I am writing here AGEFP. Okay. You see this is a correct property, because this is, you can think about, I have, this is my formula, right, this is my phi, right. So, then anything, if this formula phi is a correct CTL formula, then I can say AG phi is also a correct CTL formula. So, this is a correct CTL formula, right. So, now here let us see what is happening. So, what I am saying is along all path, that is what AG, among all path globally, right. So, that means all state in that path, right, every reachable state, effectively in a path all states are reachable, right. So, AG means along all path globally, means effectively in all path in all state. Okay. EFP is true, that means from every state there exists a future state where P holds. So, this is a little bit tricky, right. Let us draw the diagram first. Let us say I have a diagram like this, tree logic like this. Okay. So, now, and these are all infinite. Okay. So, I have this. Now, what I am saying is that from in all path globally, right, that means in all state this should hold. So, let us say I have P holds here, right. I have to give a concrete example here. Let us say I have this, these are all self loop, so that it become infinite. Okay. Now, if you think about, this is my S0, this is my S1. So, now you think about the path this, right, it going like this. In this, this is S2, right. So, what I am saying this, in if I take this path, in this path in all state EFP should hold, right. I will just explain for one path and then the other part will be counterintuitive. Now, for this state I have to EFP should hold, right. This EFP should hold for this state, S0 should satisfy this, then S1 should satisfy EFP, S2 should also satisfy EFP, right. This has to hold. What does it mean? So, now you think about there exists a path, EFP means what? There exists a path in future P holds. Now, think about for S0, I found this path where P holds. So, there exists, from here there are two paths, in one path P holds. What about S1? Again for S1 is also true, because there are two paths, in one path this holds, right. Similarly, for S2 it is not the case, because it is not happening. To make this true, you have to put P here, right. So, if I put P here, so from S2 there are only one path, S2, 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 where P holds in future, right. So, if this is the mapping P and P, I will say that for this case this AGEFP holds, right, because in this path all state in future is happening. Now, similarly, for this case also, in this, if this is S3, S3 also satisfy EFP, right, EFP. So, this part is done. Now, let us say I have P holes here, right. So, now if you think about in this case, there are many paths, right. So, in all path in future P should hold, right. So, let us say P holds, P holds, P holds here, then this will automatically hold, right. If you think about this path, in this path always you find a future state P, where from every state you will find a future state this, where P holds. Similarly, for this path, in from all state you find a future state P, where P holds. Similarly, for this case there is a future state where P holds. So, that means all state in this part of the tree, let us say this is S4, S5, S6, S7, S8, S9, S10, S11, I can write that all Si satisfy E F P, where I is basically 0 to 11. So, if this is the scenario, I can write A G E F P, right, because in all computation path globally E F P is holding, right. So, this is you have to understand carefully, right, understood. Okay. So, the next one is E G P. It is basically there exists a path in which globally P holds, which is very easy to understand. So, you basically think about a computation tree like this. It can be anything, right. So, you have to find one path in which globally P holds, right. Let us say this is my path P, 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 P and P. So, this is the path in which globally P holds, right. Then I can say this model S0 satisfy E G P, right, because I found one path in which globally means in all state P holds, right. So, this is understood. So, this is one more. So, this is effectively saying that along all path in future AGFP holds, right. So, this is another example where I am trying to say that along all path in future, right, AGP holds, right. So, along all computation path system eventually reaches state from P remain holds forever. Let me draw a diagram, computation tree. Let us say I have this, right, and let us say I have P holes here, P holes here, P holes here, P holes here, right, and P holes here, if this is the scenario. Now, in this case this is my S0, in this path, in all path, so in all path in future AGP should hold, right. Now, you think about from this path I reach a state like this. So, this is say S0, this is S1, this is S2. So, I reach a state in future S2, from there always P holds, right, because S2, 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 S2. So, in this path, right, in this path I would say that AGP holds, right, in this path starting from. So, it is basically you have to understand that AF AGP. So, that means in this path I reach a state S2, from there globally it holds, right. So, if I think about a path S2, S2, S2 and so on, that path pi satisfy GP, right. So, this is all path, here there is only one path, right. Now, here even for this path again I reach to this say S3 and then S3, 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 that is satisfying path satisfying GP. And from so it is important to understand that you reach a state where P holds, from there in all path it should hold. So, I reach a state S3 where P holds, and from there in all path P holds, right. So, because there is only one path. Now, this part is interesting. So, here I reach a state, say this is S4, in S4 P holds. From here whatever the path starting. So, this is one path which is repeating here, and this is another path that this is repeating. In both case P should globally holds, and this is happening, right. So, here you can think about this state P holds always, in this case also P hold always. So, then I can write that in this model S0 satisfy AF AG P. It means in all path in future I will reach a some state where P holds, and from there from that position all state P should hold, right. In all path in all state P holds, and that is happening here. Okay. This is the last example. So, here I basically take the negation can happen beyond a CTL formula, because if a formula is CTL, the negation is also a CTL formula. So, what I am saying here, there does not, so this part means there exists a path in next state P holds, and here I am saying there does not exist such computation path. So, this is very easy to show. Let us say I have this computation tree, and P does not, say P holds here, P holds here, right, but P does not hold in this state or this state. and this is my S 0. So, now I can see that this next state P does not hold, in this next state P does not hold. So, there does not exist any path in which next state P holds, and then I can write this model S 0 satisfy negation of E x P. Okay. This is understood. Okay. So, to summarize what we have understood, we understood what is CTL, the basic syntax of CTL, and we have taken very quite few examples and tried to visualize their interpretation with a branching tree. Okay. Thank you.